Sorry, good morning, everybody. I hope everyone had a good weekend, and I had a nice weekend. So, anyway, this is the second of our two lectures about the theory of Riemann-Hilbert problems. And just to remind you a little bit of what we talked about last time, we defined properly what the Cauchy integral is on a loop in the complex plane, suitably defined loop in the complex plane. And we talked about its boundary value properties, and we defined function spaces that are relevant in that setting, and proved some key results in terms of the Cauchy boundary value operators as bounded operators on these function spaces. And that's something that we will use going forward. So the thing we finished with at the end was this. This was a formulation of a kind of general Riemann-Hilbert problem. So remember that we always use the subscript plus to refer to taking the boundary value on some contour arc from the left by its orientation. Minus is from the right. So sigma is an admissible contour in the complex plane, and V, which is defined on all the points of sigma except some exceptional points, like self-intersection points, and is an n by n matrix. That's an admissible jump matrix with polar exponent mu. And that is referring to the smoothness properties of the matrix V along any arc of this contour. The determinant of V should be equal to 1, and then there's a certain compatibility condition that the various limits of V on incoming arcs at any self-intersection point must have. I will remind you of that condition later, but that's what it means to be an admissible jump matrix. So anyway, so we're looking for M, an n by n matrix defined as a complement of our admissible contour, which is analytic. All the elements are analytic functions in that domain. The analytic function M is going to extend continuously to the boundary, which is this jump contour sigma, from each component of the complement. And it's going to take boundary values which are defined in this way. So we have a plus boundary value and a minus boundary value by local orientation. So that's what's defined by this limit on the right-hand side. That makes sense at every non-exceptional point of our jump contour. And then boundary values are meant to satisfy this jump condition. So M plus is always equal to M minus times B of Z. And finally, M of Z, so I would just like to point out, all of these conditions so far are homogeneous conditions on the matrix M. And so we absolutely need some kind of normalizations in order to have a unique solution. And we will take that M of Z tends to the identity matrix, n by n identity matrix, as Z goes to infinity. And so the data for this Riemann-Hilbert problem is just the pair sigma, the contour, and V, the admissible jump matrix. Okay. So we showed last time that this problem has at most one solution, right? And what else did we show? And it has determinant one, right? The solution we determine if it exists. Okay. Well, so now I want to start to formulate some kind of an equation that's behind this Riemann-Hilbert problem. And for that, we have to sort of modify a little bit our definition of an admissible contour. So now we have the notion of a complete admissible contour. So if we take an admissible contour sigma, we can call it complete if it has the additional property that it splits the complex plane into two disjoint regions, omega plus and omega minus. In other words, the complex plane is just the disjoint union of omega plus, omega minus, and the original jump contour sigma. And if also sigma can be simultaneously considered as a collection of loops, which we will call Lj plus, each of which is the positively oriented boundary of a component omega j plus of the plus domain. And simultaneously, we should be able to view sigma as a collection of loops Lj minus, each of which is the negatively oriented boundary of a component of omega j minus of the minus domain. I will show you some pictures soon, okay? But that's the idea. So this contour is somehow a collection of loops that bound plus domains and loops also that bound minus domains with opposite orientation. Exactly one of these domains, omega j plus or minus, is unbounded. It contains the point at infinity. And we may note that at each exceptional point, z naught of sigma, there's going to be, in this case, an even number of components of the interior sigma circle that meet with alternating orientation going around the point z naught in the positive direction. So in, out, in, out, in, out as we go around the point z naught. Without any loss of generality, it turns out, so this seems like a new definition, but I want to tell you that without loss of any generality, you can just assume that the Riemann-Hilbert problem that we're talking about is formulated relative to a complete admissible contour. And the reason for that is because it's very easy to complete any admissible contour, and I will now explain how that works. So, given an arbitrary admissible contour, sigma 0, say, we can produce a complete admissible contour, sigma, just by adding some additional arcs as necessary. And if necessary, we may also have to reverse the orientation of some of the components of the contour. And so I will show you the picture soon, but when we do this, we don't want to change the Riemann-Hilbert problem in any essential way. So what that means is if we put in a new arc somehow to complete the contour, we should make sure that there's no jump across that arc. So we'll just put the identity matrix as the jump matrix on the new arcs, okay? And also, if we are forced at any point to change the orientation of some arcs, then we should just replace the jump matrix by its inverse on those arcs, okay? And that makes sure that we don't change any of the essential properties of the Riemann-Hilbert problem. So that's what it says over here. It's easy to check that the new jump matrix is still an admissible jump matrix, but now it's relative to a complete contour sigma, and we've not changed the jump conditions in any essential way. So that means that the Riemann-Hilbert problem, the original one, with data sigma 0 and jump matrix v0, it has exactly the same solutions as the one with the complete contour sigma and the corresponding jump matrix v. So we're going to assume from now on that we're just working with an admissible, completed admissible contour. Okay, so here's just a picture. So maybe you remember in the last lecture we had an admissible contour, which was just the union of these two arcs here, and it had exceptional points which are have little circles on them here, so 6 exceptional points. So this contour can be completed just by adding 2 new arcs. So we'll add an arc over here, and we'll add an arc over here, okay? And then on the arcs that are in let's see, so the arcs that were in the upper half plane retain their orientation. The ones in the lower half plane, you see have swapped the orientation like that. And these new arcs carry a particular orientation to make sure that we have the correct completeness property, so which we can now see. So there's the omega plus domain consists of this region up here and this region over here. And you can see that this contour is really just 2 loops, okay? Each loop surrounds one of those 2 components of omega plus, and always in the positive sense, okay? Counterclockwise orientation. So here's one of the loops, and here is the other loop. But at the same time, this contour could be considered to be the boundary of the complementary domain, omega minus, and now those loops have the other orientation. So here's a component in here of omega minus, and you see we have the clockwise orientation there. And out here, there's the unbounded part is another component of omega minus. And again, we have this clockwise boundary. Okay. So that's how we can see that this single contour can be considered as either 2 plus type loops or 2 minus type loops, depending on how we choose to think about it. Okay? So that's a simple example. So I was going to show you how to check that we can extend the jump matrix. I think I'll skip the details of that, but just remind you that this is this kind of compatibility condition that we're always going to be assuming is true for our jump matrix at any of these exceptional points. So the product of the limiting values of the jump matrix as we approach the exceptional point multiplied, or I should say raised to powers plus or minus 1 depending upon the orientation in or out. That should multiply to the identity matrix. Okay. All right. So, all right, so now that we have this notion of loops, what I want to do is I would like to define some corresponding function spaces for somehow loops associated to a jump contour. Maybe I will say something right now about where we're going with this. So the notion of solving a Riemann-Hilbert problem may be considered as taking this matrix function v, which is given on the jump contour, and factoring it into a part which is analytic in the plus domain and another part which is analytic in the minus domain. You may think of it like that. And that's a difficult problem, but what's easier might be to factor the jump matrix into a part which is simply continuous along the boundary of the plus domain, and another part which is continuous along the boundary of the minus domain. That's part of the way toward having an analytic extension into the domain itself, and that's sort of where we're going with this. We would like to define such continuous factorizations first, and then later we will turn that into an analytic one with the help of an integral equation. So, here's the definition. So let's denote by h nu plus or minus of this complete contour sigma. So we're assuming now that sigma is a complete admissible contour. So h nu plus or minus of sigma is the Banach space of n plus or minus tuples of matrix functions f1 through fn plus minus, such that these fn's, fj's here, lie in the space h nu of the loop lj plus minus. So remember, we're splitting our contour into either plus loops or minus loops, and in the case of the plus loops, we're looking for functions which are, an n tuple of functions, each of which is Hilbert continuous on that corresponding plus loop. Okay. And the norm on this space is just gotten by adding up the separate norms of these components over here over all of the loops. So f1 is supposed to be a function which is Hilbert continuous on the loop lj1 plus minus, and this is the norm on that loop, and so on, and we just add them up. Okay. So every element of this h nu plus minus sigma space, you may think of it, if you like, as a matrix function on the contour, provided that you let this function have different values at these exceptional points that are common to multiple loops. So if it turns out that a function in the plus space, so this is something which is Hilbert continuous on all the plus loops, if that agrees with a function in the minus space away from the exceptional points, so then it can be considered as either a set of Hilbert continuous functions on the plus loops or on the minus loops. And that's another way of saying that it admits a single value Hilbert continuous extension to the entire jump contour sigma. And hence, we can identify it with an element of just the Hilbert space defined on this set, which is the full jump contour sigma. On the other hand, it's very easy to see that if you have such a function, which is Hilbert continuous on the whole jump contour, then just by restriction to the plus loops or the minus loops, you can simultaneously view that function as an element of the plus space by breaking it up into the separate loops of the plus type, and also in the minus space. So that means that this Hilbert continuous set of Hilbert continuous functions on the whole jump contour is nothing but the intersection of these two Hilbert spaces. The ones that are continuous on the plus loops, the ones continuous on the minus loops. Okay. All right. So now having kind of broken this contour up into the separate loops, what I'm going to now do is kind of remind you of some of the things that we proved last time for loops, but now I'd like to just rephrase them in terms of this complete admissible contour and all of the loops together. So these are sort of analogs of the basic results for Hilbert continuous functions on loops. So in these statements that are about to follow, sigma is a complete admissible contour. So here's proposition 1. Let nu be less than or equal to mu. These are Hilbert exponents, so between 0 and 1. Then the inclusion map, I mu to nu, which this is the map which can be defined from h mu plus minus sigma to h nu plus minus sigma, or from h nu of sigma to h nu of sigma. So this is a map which is going to be compact as soon as this exponent nu is strictly less than mu. So that's just a straight analog of what we had for a single loop before. It's just now that we're considering many loops together at the same time. Proposition 2. Suppose that M is a function, a matrix function, which is an h nu plus minus of sigma. So then we may think about right and left multiplication by this matrix function M. That's what these operators were referring to in the last lecture. So these operators are going to be bounded on h nu plus minus, and also from h nu sigma to h nu plus minus sigma. So what's happening here is that the target space in all the cases is where this matrix M lives. That's not right. That's not right. I'm sorry. So the target space is somehow the worst possible space. That's what I mean to say. So if you have something which you take an input which is an h nu plus and you multiply by something in h nu plus, then you end up in h nu plus and so on. Okay. If M is in the intersection of these two spaces, which is the Hilbert continuous functions on the whole jump contour, then Lm and Rm, left and right multiplication operators, they're bounded on the same space, and they're also bounded on the plus space and the minus space separately. So that's what I mean is here we're starting out with something which is very nice. It's Hilbert continuous on the whole jump contour. If I multiply it by a plus function, then I'm going to get a plus function back out again. Okay.
Sorry,
yes.
So this x nu, if you are in the x nu space, it means that the number of positive loops and number of negative loops will be the same, right?
Not the number of loops, but so if you're in this this space here, then what it means is that if you view your matrix function, which is defined on the whole jump contour, as being separately defined on the plus loops, then on each plus loop it's Hilbert continuous. At the same time, if you choose to view it as a function defined on each of the minus loops, on each such loop it's again Hilbert continuous. That's what that means. That's being in both of the spaces together, right? It's the intersection. So a given loop is either a plus loop or a minus loop, but not both. Yeah.
But your jump is a function that defined on the whole loop. So why would it be in h plus but not in h minus?
So let's look at the picture again. Here's an example. So I'll show you some concrete example in a minute. But you know, if you have a function which you may think of as being continuous along this curve where I'm tracing the laser pointer, right? So in particular, the value coming in here is the same as the value going out there, right? But anyway, there could be another such function defined on this loop, and that may have nothing at all to do with this one. So then that means that there's a discontinuity in the matrix function defined on the whole contour, and yet still it's continuous along this loop and it's continuous along this loop. This one is not. This one will have a jump discontinuity.
So at the end points.
Yeah, at these points, at these exceptional points. Yeah. Okay. I'll show you an example soon. Okay, so that's the multiplication operator result. Then there's the generalization of the Plumel-Pribilov theorem. That's the one that in the loop case it asserted the boundedness of the Cauchy operators C plus and minus on a given loop. So suppose that nu is between 0 and strictly less than 1, so we cannot, again, we must not allow the Lipschitz condition. Then the Cauchy operators C sigma plus minus, they're bounded on the space h nu plus minus of sigma. And this is kind of interesting. They're also bounded from h nu minus plus to the better space h nu of sigma. So if you start with something that's in h nu minus and you apply the C plus operator, you're going to get something which is better. Okay. Okay, it's actually going to be Hilbert continuous on the whole space. You'll see an example of that. And then on the union of the plus and the minus spaces, no matter where you're working here, then you have the following operator identities. So this is again the Flamel formula written in operator notation. This is the one that says that these C plus and minuses annihilate each other on the jump contour. And then this condition says that plus and minus, plus or minus, C plus or minus, is a projection operator. So taken together, this and this say that C plus or minus, C plus minus are complementary projections that add up to the identity. Okay. So the fourth proposition deals with commutators. So suppose now that mu and nu are between 0 and 1. So if m is a function in h mu plus, so then the commutator is c plus minus with left multiplication by m or right multiplication by m. They are bounded from h nu plus, h nu minus, or h nu to the place where m lives. Okay, that's what I'm saying here. So the target space is the place where m lives. The input space could be any of these. And respectively, if m is in the minus space, then the target space is going to be the minus space. And if m lives in the intersection of the two, so it's polar continuous on the whole contour, then again these commutators will be bounded to that space as well. So you always end up with the commutator. You always end up where the matrix M lives. That's the point. Okay, and if you take, if you're in the case where the nu is strictly less than mu, then you can follow the commutator by the inclusion mapping, which is compact in that situation. So then all of these commutators are compact maps. Okay, so if we're going from, if our m is a little bit better of a function than the inputs are, then we're going to have a compact commutator map. So those are all just almost word for word statements, slightly different in terms of the target spaces, the plus and the minus. That's the only difference with statements that we showed last time for loops. And I just want to mention the proofs of these propositions. They are just straightforward analogs of the ones that we have for loops. It's just that the Cauchy operators now have contributions from many loops, and you have to add them up. Okay, so you just have to account when you're adding things up for the way in which the boundary values are being taken, and that tells you which spaces they end up being in. So I'm not going to go through the details of that, but it's straightforward, just keys. So here's another useful fact that we'll have an opportunity to use later on. So suppose that f and g are both in either h plus or h minus. Okay. So then let's define capital H plus minus of z to be the pointwise product of the Cauchy transforms, so c plus minus of f and c plus minus of g, like that. So here the side on which we're taking the boundary value is the same for both factors. That's the point. And the functions can live in either space. So then c minus plus of the product h plus minus is exactly 0. So this is similar to the proof that c plus following c minus is 0, which is similar proof. So the function h plus minus is the product, as you can see here, of boundary values of functions analytic in omega plus or minus. And if there's an unbounded component there, they decay, those two factors decay like 1 over z as z goes to infinity. So that means that h plus minus is also an analytic function in the domain omega plus minus, but it decays like 1 over z squared as z goes to infinity. So now to calculate this thing, we're going to take c minus plus. The first thing we do is we let z be in the complementary domain, omega minus plus. And now we just apply the generalized Cauchy integral theorem to deform all of the contours into the plus minus loops. Okay? And then you're going to get 0 just by the residue theorem. Okay? And so now the limit of 0 is 0 when we take the limit of the point z, which started out in the domain omega minus plus, and let it tend to the contour sigma. So that's really the same argument that we used to show that c plus following c minus is 0. Okay. That I think we'll use that later. Okay, so now I promised the example, so I want to sort of illustrate a little bit how this works. So again, here's our completed contour and domains omega plus 1, omega plus 2, and then the loops that surround them in the positive sense, and then omega minus 1 and omega minus 2 in the exterior with their boundary loops surrounding them in the negative sense. Okay, so now let's consider this function. We're going to define a function on this thing with these two exceptional points omitted. And that function will be taken to be just exactly 1 on the boundary of this component here. So f of z is equal to 1, it's equal to 1. And here it's going to be minus 1 and minus 1, okay? That's all. So everywhere in the upper half plane, f is 1, in the lower half plane, f is minus 1. So this function can be thought of as an element of the space h nu plus, because if I restrict to this loop, then I have the constant function 1, which certainly is polar continuous with every exponent. And down here, on this boundary of this loop, I have f of z equals minus 1, which is again a constant, and it's smooth as you like, so it's definitely in the polar space. Okay. But the same function f is definitely not in the minus space, and that's because there are jump discontinuities along the boundary of, say, this component, right? So this is a loop L1 minus, and here we have plus 1, and there we have minus 1. So there are jump discontinuities at these two corner points of that loop, okay? All right, so now let's calculate the Cauchy integral of this f, because what we want to illustrate is how these mapping properties are going to work, okay? So it's easy to calculate the Cauchy integral. There's just a bunch of cases. You sort of think about where z lives, exterior, here, or here, right? And then you do some residue calculus. So, for instance, if z is in this domain here, then I apply the residue theorem, and this one here gives me 0 if I integrate over this loop, and if I integrate over this loop, I'm going to get 1. And so the answer is 1, as long as I'm in the interior of this domain. Likewise, if z is over here, then I'm going to get minus 1. And then anywhere else, if z is in the minus part, anywhere, okay, now I may just use the Cauchy theorem to take this integral here, and it's going to be 0 because z is outside. And likewise, if I integrate on this loop and z is outside of that loop, I'm going to again get 0. So in either case, if z is in the minus domain, the answer is 0. Okay? So now, if you let z tend to the contour from the plus domain, right? So if I'm in here and I go to the contour, I'm going to take the limit of 1, which was our answer for being inside here, and I'm going to recover the original function f that we had before. Likewise from the bottom here. If I'm in this domain, I take the limit of minus 1 and I get the same answer. So that, remember, this function was in the plus domain. I applied the C plus operator to it, and I got back something in the plus domain. So that was guaranteed by the general proposition. But remember, if I apply the minus operator to a plus function, I should get something better. So let's check that. So now I'm going to tend to the contour from here. So here, the limit, here the answer was 0, right? Anytime I'm in the minus domain, the answer to our Cauchy integral is 0. So I take the limit of 0 and I get 0 here and here. If I'm on the outside, I take the limit, I get 0 here and here. So this function C minus of our function f is just identically 0. Okay, and that's the best function in the world. So it's obviously in both h plus and h minus. So it's in our whole, it's polar continuous on the whole jump contour. So C minus of our plus function f is in h nu of sigma. Okay, so again, that was one of the general results that's guaranteed by the proposition. Okay, just to illustrate by some very simple residue calculus example. Okay, any questions about this one? Yes.
The assumption in factorization time computer is FG is either in
right. In either space. Yeah.
Actually, FG defined on both spaces. Both loop has some meaning
So either f is either f will be a plus function or it will be a minus function. Likewise, either g will be a plus function or a minus function. That's what it means.
I know what you mean.
Right, and then we take those functions and we calculate a consistent choice plus or minus of the Cauchy boundary value for both cases.
If I were you, I would replace the cosine by cat.
No, I don't want to do that. No, definitely not. I mean, it's also true in that case, but it's true in this case as well. So we're just integrating over the loop. When we calculate these integrals here, we just integrate over either the plus or the minus loops, depending on whether f is in this space or that space. Yeah, that's how we do it. Yeah.
So if suppose f is in plus and g is in minus, then when you do the Cauchy integral, you need to consider also plus and minus. Is that right?
So either way, once you compute this Cauchy integral, it's analytic in the whole complementary domain, right? And so moreover, since we're taking the same index plus or minus in this product here, right? Each factor is going to be analytic in the same domain, either omega plus or omega minus, depending. And that's the one where I compute this Cauchy integral with the opposite index. So the opposite sign. Okay, so I mentioned that the baby step towards solving the Riemann-Hilbert problem, which is somehow factoring the V matrix into analytic factors in the omega plus and omega minus domains separately, the baby step is to just factor it into something which is continuous along the plus loops and something else which is continuous along the minus loops. So that's a kind of algebraic factorization of the jump matrix that we call an admissible factorization. So suppose that sigma is a complete admissible contour and V is a corresponding admissible jump matrix with Hilbert exponent mu less than 1. So then we say that sigma comma B plus comma B minus, that's an admissible factorization of the Riemann-Hilbert data sigma V, provided that we can express this V of Z as the matrix product of B minus of Z inverse times B plus of Z at every point where the V is defined. That's the every point except the exceptional points of the jump contour. And then the B plus and the B minus of Z, those are supposed to have determinant 1, and B plus is supposed to be an H plus function, and B minus is supposed to be an H minus function. Okay, that's what it means to have an admissible factorization. This is the baby step towards solving the Riemann-Hilbert problem. Somehow factor your jump matrix into a plus function and a minus function. Okay, there's an inverse here, but this thing has determinant 1. So that's the idea. Okay, so if you can do this, well, there's lots of ways to do it. So these admissible factorizations are not unique. If you have one, there's a very simple way to produce another one. But maybe I won't use that back going forward, so we'll skip that. But what I want to say that's important is that it's not difficult at all to have an admissible factorization. That's a relatively straightforward thing. And we can build one using a technical lemma like this, which we call unimodular determinant 1 interpolation. So suppose that A and B are matrices that have determinant 1. So then there exists some matrix function from 0, 1 to n by n matrices that's a C infinity function that's equal to A at the initial condition 0 and equal to B at 1. Okay? And determinant of f of t is exactly 1 for all t. So you can get from one matrix to another with determinants equal to 1 in such a way that the determinant always remains 1, and so that the matrix function that gets you from the A to the B is very, very nice. So the construction might be based on the Jordan canonical form of the matrix A inverse B. So we have some generalized eigenvector matrix here, so we conjugate A inverse B into a diagonal part that has all the eigenvalues of A inverse B, and N is a nilpotent part. It's like upper triangular. It's the Jordan part. Okay. So then we choose some numbers L1 through Ln, whose exponentials, which we will say those are the eigenvalues of the matrix D, and those are non-zero because D is a matrix the eigenvalues, the diagonal entries of D are precisely the eigenvalues of this matrix, and that one has determinant 1. Moreover, because the determinant is 1, the product of the eigenvalues is 1, and that means that these L's have to add up to 0. Okay, so L is like for log. Okay, it's like the log of the eigenvalues. So then, having picked such things, then we take the eigenvalue matrix like this, put the eigenvalue, the logs of the eigenvalues in the diagonal matrix, and then we define our f of t in this way. So we put back the a factor, and then here we just have the conjugation again of exponential TL plus t times the nilpotent part. Okay, so then you see that when t is equal to 0, this one is not there. This is identity matrix, and so I have a. And when t is equal to 1, then I'm getting exactly the exponential of L, which is D, and then plus n. So I have this, and that's A inverse B, and the A is killed, so that's just B. Okay, so clearly f of 0 is A, f of 1 is B, and f is infinitely differentiable. And so finally we can calculate the determinant of this thing as just the determinant. Well, the determinant of A is 1, the determinant is just this part in here. And that's just the product of these eigenvalues, so that's 1. Okay. So here we're using the fact that this is nilpotent. Okay. So anyway, so just a formula, but now we have a way to get from one point to another, one determinant one matrix to another, and so now yes.
That's L.
Yes.
Do you need to worry about the assignment of branch part?
So I'm just gonna choose some numbers, okay? So it doesn't matter how you do it. I'm going to choose some logarithms, and that in itself is a well-defined notion. Sorry, what I want to say is the fact that I may choose these logarithms is just because these d's are non-zero. But you're right. There's some ambiguity in how you choose it. It doesn't matter how you do it. This formula will give you a. I'm not saying that this is the only way, but this gives you an interpolation of the desired properties. Okay? So you might choose different L's than I choose.
Well, essentially, there's just d to the t power.
Sorry?
I mean, if you use the original notation, it's just d matrix to the t power.
Yeah, that's right. It's d to the power t, right? But that's ambiguous, so, as you said. Okay, so now I would like to use this lemma to construct a specific type of admissible factorization that we'll just call a standard factorization of Riemann-Hilbert data sigma b. So first of all, there are these exceptional points in our jump contour X where we could have self-intersections and so on. And actually, not all of those are going to cause us headaches. The only ones that are going to cause us headaches are those points, those exceptional points, where the limits of the jump matrix coming in from all the different arcs is not always the identity matrix. Okay, so let's just say that x0 is the subset of those exceptional points x, where at least one of the jump matrix limits at the point z0 is not the identity matrix. So we only have to worry about the x0 points as it will happen. The other ones are going to be okay. So let's isolate each point z0 in that x0 set. Let's isolate each such point by letting d of z0 be a disk centered at that point of some small radius, okay, so small that it contains only z0 and k arcs that are joining z0 to the boundary, partial d of z0. And in particular, D of Z naught doesn't contain any other points of X naught. Okay. So we start out to define our admissible factorization by just setting B plus, the B plus factor, exactly equal to the jump matrix, and B minus factor exactly equal to the identity everywhere outside of these disks. Okay? So it's the simplest idea. You just ignore the B minus part if you like, and outside of all the disks, we'll just take that as our factorization. Okay, so now what we have to do is worry what to do inside of these disks. So for each point Z naught in this set X naught is of exceptional points where the limits of the jump matrix are not all the identity. If we intersect the jump contour with that disk, then there's an even number of arcs that join the boundary of the disk with the center of the disk. And the orientations, we said, are going to alternate in and out. Okay? So let's order them in some counterclockwise order around Z naught. We'll call them C1, C2 through CK. Maybe I'll take a picture of that. So here's the point Z naught. So then here is a C1. Maybe C1 is like this. And then C2 is going out the other way. And C3 comes in, and so on, like that. And there's an even number of them, okay? So the last one should be going out rather. And this is CK. K is even. Okay. And then I also have my disk somewhere. So here's my disk. This is D of Z naught. And so each one of these arcs just meets the boundary of this disk somewhere and goes in towards Z naught like that. All right. So we assume that C1 is oriented towards Z naught as I drew in the plot over here. So now let's take a smooth parameterization. Z is equal to Zk of T, T going from 0 to 1 for each of these arcs. Okay, and we'll choose the parameterization to be just some constant multiple, perhaps a different multiple for each arc, but anyway, a constant multiple in each case of the arc length parameter. Okay. So then let's observe that Zk of 0, that lies on the boundary of our domain, and Zk of 1 is equal to the center whenever k is an odd number. So here, Zk of 0 is this point, Zk of 1 is this point, right? For k equals 1. For k equals 2, it's the other way around. That's because for the evens, Zk of 0 is the center, and Zk of 1 is on the boundary. Okay. So that's just the alternate orientation. Okay. So now, let's now figure out how are we going to define these groups. Okay. How are we going to define these factors B plus or minus on these different arcs? Okay. So we know what B plus is outside. It's the same as the jump matrix V, and we also know what B minus is. It's the identity matrix. So somehow we have to continue that factorization in a nice way inside of this disk that is somehow respecting the Hilbert continuity properties around the different domains, the different loops. Okay. So the first thing, let's just start with C1. Okay. So by some kind of natural continuation, let's set B plus equals V, and B minus is identity. So that's what we're doing here. So here's C1. So B plus is V, and B minus is identity. That's what we'll do. Okay. So actually, the arrow is coming in here. So I guess I wrote the B plus on the plus side by orientation, and I wrote the B minus on the minus side by orientation. Okay. Yes.
Usually, the identical is outside.
Yes. Right. So this is just right. Exactly. So out here we also have B plus is V and B minus is identity. But that's also what I have over here. And outside for all these, right? As soon as I'm outside of this disk, I have that B plus is V and B minus is the identity matrix. Okay? And now what we did here is we said, well, let's just extend that definition in along the arc C1. Okay? But now I have to figure out what to do with these other ones, and that's what I want to explain next. So suppose that I'm going to treat it like an induction idea. So suppose that we define b plus or minus on the arc ck minus 1. So here I guess k is equal to 2, right? And k minus 1 is 1, so we've defined it here. And now I want to extend the factorization to ck, which in this case is c2. In such a way, okay, that these b plus and minus matrices are going to be locally continuous close to the point z naught along the boundaries of omega plus and minus respectively. Okay, that's what it means to somehow be a plus and minus function. Okay. Okay. So all right. So if k is even, like it is, if we start with k equals 2, so we were trying to get to this c2 here. So if k is even, then we see that there's a component of the minus domain that lies between ck and ck minus 1. So that's exactly what's happening here. This is a minus region in here, right? You see that the boundary is going around omega minus in the clockwise sense, and so that means that this is a piece of the minus domain. Okay. So what we need to do here, what's really essential, given that I've got b minus is the identity here, I need to make sure that that this b minus function is continuous, at least along the boundary of the minus domain. Okay. So what I'm going to do is I'm going to start out with b minus equals identity at this point, and then I have to connect it to whatever b minus is at this point. Well, that was also the identity, right? So here b minus is identity outside. So I'm taking b minus as identity here in order that I have continuity like this around the corner. And now it's very easy to connect this to that, so I'll just take again b minus to be the identity along that next piece. Okay? Now, having done that, I don't get a choice about what b plus is, because b minus inverse times b plus should be equal to v. So here I have to take b plus again equals v on this one. So now on C2, I've just continued my on C2, I've just continued my factorization, and it looks kind of the same as what I had on C1. But now if I go to the next one over here, right? Now at this point I have a plus domain that's in between. And so what I need to do is I need to ensure the continuity around the corner here of the plus factor. Okay? So the plus factor was equal to v as defined on this arc. Okay? So I need to use exactly the same value here. So this is b, okay, let me just say, in this corner here, okay, b plus is going to be equal to this limit as z goes to z naught for z in this arc C2, okay, of v of z. So I'm going to take that value in the corner here, and when I want to go back out along this one, I have to get to the value b plus equals v at this point from the one over here, and so I should smoothly interpolate between those two values. So now I'm applying this interpolation idea. I'm applying the interpolation idea to get between z0 and the boundary of the disk. The boundary of the disk out here. So that's happening. I guess I'm doing this case now. So I'm getting to the boundary of the disk. I start with v at zk of 0, and I need to get out to b plus at the other side. And so I'm going to take that factor. I'm going to take that interpolation and continue use the interpolation to continue the plus factor now. Sorry, out here along C3. And once I've done that, then I have to calculate what the minus factor is using, again, this identity here. This identity has to hold at every single point. So in each case, what I'm doing is going around the corner. As I go around the corner, I have to make sure that I maintain the continuity of whichever factor it is that is corresponding to the domain which is in the wedge. So in this case, I have to have the continuity of the plus factor. In this one, it was the continuity of the minus factor. And then I get to the boundary where I have the definition in place using this interpolation lemma. Okay? So in the end, what you can do is systematically work your way all around with this construction And the thing you have to wonder about is what happens when you get back to where you started. Okay? So the fact that this factorization is admissible, it boils down to showing that these b plus or minuses are plus or minus functions, and so the continuity will follow from the construction that we just built, provided that we have this kind of compatibility. When we get around the whole circle and back to where we started, we get the same answer. And that what's happening there is it's this identity that we talked about, this product identity of the jump matrix that guarantees that that procedure works. Okay? So the compatibility of the original jump matrix around the self-intersection point is the thing that guarantees that this construction actually gives you a consistent result inside of this disk. And then at the end, each time you go along the boundary of a plus region, it's the plus factor that's continuous at the junction point. And if it's the boundary of the minus region, it's the minus factor that's continuous at the junction point. Okay. All right. Yeah.
So you use enthalpy theory to extend the definition on each control. For example, C3.
Yes.
If you just define it, the big part on C3 simply naively by V.
Because the V value along this curve has nothing to do with the V value along this curve.
But can we just set it to V? No?
No, because that's what I'm saying. So the only thing we know about V, aside from the fact that it's smooth on each of these arcs separately, is that once we consider their limiting values at this self-intersection point, the product of all of them in going order is the identity matrix. But they are all different. And so if I tried to just take the same V and go back out again, I would have a jump around the corner here, which I can't admit. I have to make sure that the plus factor is continuous there. So I have to take for the outgoing plus factor here, I have to take whatever was coming in over there, and then I have to match it on to whatever was out here already, which is the original jump matrix. Those are not the same. That's why I can't just use V.
So in the liquid factors, V minus are all continuous at Z0.
In the sectors that are the boundaries along the boundary of a minus component, B minus should be continuous at the junction point.
Not necessarily B plus.
But B plus doesn't matter, right? And then along the boundary of the next one, that's a plus part, and then I need the plus factor to be continuous. And I don't care about the minus. Right? Mm-hmm. That's right. So that's how you can build something inside of each one of these disks that is that's compatible with the definition of admissibility for the jump matrix. So of the factorization. I'm sorry. So what sort of properties does the standard factorization have? So one thing that's interesting is that if the jump matrix is close to the identity matrix, say in the Hilbert mu sense on the various arcs of the jump contour, then you can show that the B plus and minus take away identity. These are also small in the mu plus the plus minus norm. So if you add up the norms over the plus loops of B plus minus identity, that's going to be small if this was small to begin with. So in fact, if you take some concrete choices of the different parameters, so we have the radius of these disks, which might be slightly different for all the different points in X naught, the interpolating function, which we already said there's some potential ambiguity in how you define that. But anyway, if you settle those things, then you can prove an estimate like this, that the norm, the plus norm of B plus minus identity, is going to be bounded by some multiple of the mu norm on the interior arcs of B minus identity. So in other words, this factorization is somehow not messing up the property that B might be close to the identity matrix, and that's a good thing here's another even simpler property that is handy in some applications. So suppose that sigma is a complete admissible contour, and V is a corresponding admissible jump matrix with a Hilbert exponent less than 1. And suppose that it also has the property that for some point Z0 in the jump contour, some exceptional point Z0, self-intersection point, say, V of Z is identity plus order Z minus Z0 to the power P. So V is sort of decaying to the identity matrix as we approach Z0 along any of the arcs that meet at the point X. So then, if you apply a standard factorization, it's also going to hold that B plus and minus are both identity plus order Z minus Z0 to the power P. So this seems like it might be complicated to show, but actually it's trivial because you see the fact that V goes to the identity means that the point Z0 is not in X0, it's in the other part of the exceptional point set X. So that means that in the neighborhood of the point Z0, B plus is just V, and V already satisfies this fact, and B minus is exactly the identity. Okay. So anytime that we have V is decaying to the identity matrix, the same is going to be true for the factors B plus and minus. Okay. All right. So now I want to formulate the singular integral equation that's behind the Riemann-Hilbert problem. So we start out with sigma V plus V minus being an admissible factorization of the Riemann-Hilbert data sigma V. And we define a matrix function W plus to be just the difference between V plus and the identity. So that's a plus function on our contour. And W minus is identity minus V minus. That's a minus function on the contour. Okay. So then the key operator that shows up when we study the Riemann-Hilbert problem is this thing that's frequently called CW because it depends on these matrices W plus and W minus. So it's a sum of two parts. First is right multiplication by W minus followed by the action of the plus Cauchy operator. And the other part is right multiplication by W plus followed by the minus boundary value Cauchy operator. So if you have a function f that's defined on the arcs of the jump contour, a matrix function, then the way that this thing acts on f is, okay, multiply on the right by W minus and then take the plus Cauchy integral. Multiply on the right by W plus, take the minus Cauchy integral, and add them up. Okay? All right, so the first result about this gadget here is that CW is a bounded linear operator on the space h nu of sigma whenever nu is less than or equal to mu is less than 1. So mu, you may remember, that's the space in which the w's are within. Okay. So this is a good space. This is the one. This is the Hilbert space of functions that are just Hilbert continuous on the whole jump contour. That's the space on which the CW acts. Okay, so here's the proof of the statement. So since h mu minus of sigma is contained within h nu minus of sigma for nu less than or equal to mu, the right multiplication operator by W minus is bounded from h nu to h nu minus. That was one of our basic results, one of our propositions. And on this space here, the plus Cauchy operator is bounded, and the range is the whole space. That's like our example when we had the plus 1 and the minus 1, and we took the minus boundary value, and we got something that was 0 on the whole function in the Hilbert space of the whole contour. Right? So that's the range of this one. So likewise, if you look at the other part, multiplication on the right by W plus, that's a bounded operator from h nu to h nu plus. And on that space, the Cauchy operator C minus is bounded, and the range is again the space of Hilbert continuous functions on the whole jump contour. So we add those two pieces together, just like this, and that gives us something that maps Hilbert continuous functions on the jump contour back into the same space, and each piece is a bounded operator. Okay? All right. So now, sorry?
Why do you choose right multiplication?
It's ultimately it's because the jump matrix shows up on the right in our jump condition, right? M plus equals M minus times B. That's the reason right multiplication is showing up here. Okay. So theorem 5. This is a key result. Okay. So the singular integral equation for the Riemann-Hilbert problem. So suppose that sigma b plus and b minus is an admissible factorization of the Riemann-Hilbert data sigma b, corresponding to Hilbert exponent mu less than 1. And suppose that nu is less than or equal to mu. So then every solution x in the space h nu sigma of this singular integral equation, okay, so what's going on here? We have identity minus CW acting on x is equal to the constant matrix function identity. That's what that says. Okay, that constant matrix function identity happens to be like the function 0 in our example. It's in the Hilbert space h nu of sigma. Okay, so that's an equation which I'm considering on this function space to solve for x. So every solution of this integral equation gives us a solution of Riemann-Hilbert problem 1 by this explicit formula. So M of z is the identity matrix plus this gadget. So this is this Cauchy integral of the product x times w plus plus w minus. Or written in terms of a formula with integrals, it's this object here, okay? So every single solution x of this integral equation, if I put it into this formula, it gives something m of z that solves the Riemann-Hilbert problem, okay? So let's see why that's true. Okay, so suppose that x solves the Riemann-Hilbert, solves the integral equation. So putting that into formula 8, we get this m of z as sort of identity plus a Cauchy integral. It's certainly analytic as a function of z in the complementary domain where we're integrating. So we're integrating over sigma. And this function is Hilbert continuous with exponent nu right up to the jump contour sigma, and it clearly goes to the identity as z goes to infinity because, just to remind you here, we're integrating over this compact contour sigma, and there's a 1 over z over here, right? So this is decaying to the identity matrix. So the only thing that we have to check, really, is just that the jump condition holds, and the jump condition is this one, right? So m plus equals m minus times v, but given that v has been factored into an admissible factorization, we could write this in another way. We could write it as m plus times identity plus w plus inverse. So this was, by the way, b plus here. Okay, so m plus b plus inverse equals m minus b minus. So this is identity minus w minus inverse. That's b minus. So, okay, so that's just the jump condition written in terms of our admissible factorization, which can be broken into these w's. So now we substitute for m from the formula for m, right? So m was some Cauchy integral business. So this is m plus, okay? Identity plus the plus boundary value now of xw plus the plus boundary value, Cauchy integral xw minus, times this factor. That's equal to, on the other side, I just take the minus boundary values for those two Cauchy operators and just copy like that. So this is the integral equation, the formula for m, sorry, just written in here. But now we're going to go ahead and use the integral equation for x. And we're going to use it to get rid of this term plus identity matrix. So you'll notice this term here is just copied down here. And this plus that by the integral equation is x of z. That's the identity part of the operator, identity minus cw. And then this is the other part of cw showing up over here. Okay? And this was the right-hand side of our integral equation. So anyway, so this plus that is turned into this plus that with using the integral equation, and this just comes along for the ride. And likewise on this side, we're going to do the same thing. We'll get rid of this one and leave that one alone. So this is now coming from the integral equation. And now the last thing to notice here is that here I have c plus times acting on xw plus, and here's minus c minus acting on the same thing, xw plus. So that's the Plumel formula, right? That's c plus minus c minus is the identity operator. So this is really x plus x times w plus. That's what this expression is. And this one here, same story. This is x plus x times w minus. Sorry, x minus x times w minus. Okay, so look, this thing times that, this thing times that, that's the same thing as x equals x, okay, at the end of the day, by using the Plumel formula after we substituted from the integral equation. So that's the reason why we're getting the solution of the jump condition from a solution of the integral equation. It's really just the Plamelge formula. Okay?
So in practice,
yes.
both W plus minus and capital X depends on the way you do the interpretations.
That's right.
In the end, it cancels.
That's right. So it doesn't matter in the end. And in fact, if you have two different admissible factorizations, the CW operator is related in the two cases by some explicit conjugation. I think I wrote it here. Yeah, I mean, so if you have two admissible factorizations, then the associated integral operators are just related by a right multiplication. So in the end, it's like you say, it doesn't matter which one you pick, you're really doing the same thing. So, okay. All right. So here's another result. So suppose that the integral equation has a solution, and Z naught is a point in our jump contour at which these W plus or minuses, which are like the non-identity pieces of the B plus and the B minus factors, that they vanish to all orders, say, as Z goes to Z naught along every component of the jump contour that meets at the point Z naught. So then the corresponding, remember the solutions of Riemann-Hilbert problem 1 are always unique, so the corresponding solution, M of Z, of Riemann-Hilbert problem 1, that's given by our explicit formula in terms of X, it's got an asymptotic expansion in powers of Z minus Z naught like this. So M of Z minus identity has this power series expansion as Z goes to Z naught with all these different powers showing up and coefficients Mn, which are given by these integrals here. And what I want to say is that there's denominators. Remember, Z naught is a point of our jump contour, so there are these denominators here. But these are harmless because we are assuming that these two factors vanish to all orders as W goes to Z naught. So this is a cancellation which is perfectly reasonable here, and these integrals are all convergent. Okay, and moreover, all of these hypotheses that we have, they're guaranteed if we use a standard factorization as long as the V minus identity vanishes to all orders as Z goes to Z naught. So the proof of this is really just to truncate this series expansion and to plug it in and see what comes out. So for any m, 0, 1, 2, etc., we just expand this denominator in the usual geometric series plus remainder term. Okay, so we chop it somewhere and we keep the remainder. And now we put this into the formula for the Riemann-Hilbert solution in terms of the matrix X, and we write down exactly the m minus identity minus the m partial sum of this thing coming from this term, okay, where the coefficients are exactly as we expected, is equal to this quantity here, and the error term has this coefficient in it. Okay. So now the hypotheses on W plus or minus, they imply that this Fm is a function that's Hilbert continuous on all the arcs separately of the jump contour, so its Cauchy transform is Hilbert continuous up to the jump contour itself, and that means that this right-hand side over here, because of the factor Z minus Z naught to the m plus 1, it vanishes faster than the last retained term over here. Now I just want to remark that this is not, this expansion that we're writing here, this expansion looks like a power series, and it might converge, actually, but it's usually not going to converge to that. And the reason is just that, that generally speaking, the matrix M might, it's got to be continuous at the point Z naught because the jump matrix is vanishing, is going to the identity there. It's got to be continuous at the point Z naught, but in a neighborhood of that point, there are some jumps. So it's not even a continuous function on a neighborhood of the point Z naught in general, but still, it has this asymptotic power series expansion. So it's just saying that the jumps are exponentially close, let us say, to the identity matrix in the neighborhood of this point. Okay. Yes?
How do you interpret when this? So this C naught is in the, is the vertex of...
It could be, sure. Yeah.
And it can also be in the middle of...
It can also be in the middle. It's just, what's important here is that the factors, W plus and minus, they vanish to all orders as Z goes to that point. And as we said, that's guaranteed by an admissible, by a standard factorization, if the original jump matrix had that property. It vanishes, it goes to the identity, say, arbitrarily rapidly as you approach the points. It doesn't matter whether it's a vertex or an interior point.
Okay, so the difference is exponentially small, say something.
Yeah, something like that, right? So there's some jumps there, but they're exponentially small, and so this is not this series. Even if it's convergent, it might be divergent, but if it's convergent, it doesn't converge to that. Okay, there are somehow exponentially small terms that are missing. Okay. So anyway, so one easy way to solve the integral equation 7 and then consequently get a solution of Riemann-Hilbert problem 1 is to use this idea of iteration. So you try to just represent this inverse operator in the integral equation by its geometric series expansion. Okay, so you apply identity, and then you apply CW, and then CW after CW, and so on. So that's like an infinite series of powers of the operator CW, like this. And so, well, this operator series converges if the operator norm on the Holder space H nu is less than 1. That's what we need, right? And that's when we have that situation, we say that we're in a small norm situation. And we know from the proposition 7 that this is a bounded operator, so it's got a finite norm, but it's handy to estimate it in terms of things like the jump matrix so that we can try to be in this situation. So, so these objects here, these Cauchy operators by this generalized Plumel-Privalov theorem, they're bounded operators from H nu minus plus to H nu. And so that means that there's some constant k that only depends on like the shape of the contour, so that this inequality holds true. And so this over here, this is the norm on H nu, and on the right-hand side, these are the H plus minus plus norms. Okay. So then from there, it follows really easily that if I apply this, if I remember how the CW operator is built, then I can take out these plus norm, the plus norm of W plus and the minus norm of W minus and add them up as an additional contribution, okay? So this identity holds for all functions f in the space H nu, and so that gives us a way to measure if we have a small norm problem. If it turns out that our factors B plus and B minus have these W pieces so that the sums of these norms is less than 1 over k, then I've got a convergent operator series. And so this is basically saying that these perturbations from the identity should be small. So V should be close to the identity matrix in some sense. And some sense is like in this sense. Okay? If that's true, then I'm going to have a small norm problem. So then from this Banach algebra property of operators acting in the space H nu, then we can get an estimate on the inverse of this operator. And it's just from geometric series again. So 1 over 1 minus the operator norm of CW, which is something less than 1 under our hypothesis. That's an estimate of the norm of the inverse operator. And so since the function that's on the right-hand side has norm 1, that gives us an estimate of the size of the solution of our integral equation. Okay, now, so I want to just mention that, I'm going to mention this fact here. So small norm problems, they very rarely just happen to fall into your lap. So usually what happens instead is that you have a Riemann-Hilbert problem that has some small parameter in the data. And so you could leverage that small parameter somehow to try to convert your problem into a small norm problem, but it's not such a problem when you start. So there's sometimes you can introduce a finite sequence of well-motivated substitutions that will convert your Riemann-Hilbert problem with the original data into some equivalent one with some modified data, sigma prime and v prime. And this one is in fact a small norm problem if epsilon is small enough. And this sequence of substitutions, this is the sort of main idea behind what's called the Dave-Joe steepest descent method for Riemann-Hilbert problems. And that's what I'll illustrate later on. But for now, I just want to say that it's a great thing to have, but usually you have to do some work before you're in this small norm situation. Okay. All right. So if you're not in a small norm situation, you still would like to know maybe that your problem has a solution. And so I need to say some things about Fredholm theory. So this is, I think, referring to the textbook of Peter Lax on functional analysis. Okay, so if A from some Banach space to another is a bounded linear operator, then by definition its kernel, cur of A, that's the subspace of vectors F that are killed by the operator A. The range is the subspace range of A of vectors that are the images of other vectors under A. And the co-kernel, by definition, that's the vector space of equivalence classes of your Banach space mod the range. Okay? So by definition, an operator, a linear operator, is called Fredholm if the kernel and the co-kernel both have finite dimension. Okay? And in that case, a Fredholm operator has something defined on it called index, and the index of the operator is the difference of those two dimensions. Okay? Dimension of the kernel minus the dimension of the co-kernel. Okay, pseudo-inverse. So suppose that A is a bounded linear operator on the Banach space B. So another bounded operator B that acts on the same space is called a pseudo-inverse to A. If anytime you take B following A or A following B, you get a compact perturbation of the identity operator. Okay? So it's almost like an inverse up to some compact piece K or K prime, depending on the order of the action. Okay? That's what a pseudo-inverse operator is, by definition. So then the key result that we need is the following. So suppose that A on a Banach space B is a bounded linear operator. So then A is Fredholm if it's got a pseudo-inverse. Okay? So that's how you can tell if your operator is Fredholm. You try to build the pseudo-inverse. And this is, I think, really interesting, I have to say. So by some kind of analogy with the definition of this operator CW, you can try to, so we're going to build a pseudo-inverse is what I'm going to say for CW, for identity minus CW. And we're going to do it by thinking about the inverses of these matrices, B plus and B minus. So it's like an algebraic inverse is going to turn into an analytic pseudo-inverse. You can think of it like that. Okay? So suppose we take, so here's our B plus operator. We take its inverse and we call that U plus. Take its inverse and subtract the identity, and so that we'll call U plus. So just to remind you, W plus was just B plus minus identity. So now I'm taking B plus inverse minus identity and I'm calling that U plus. And similarly, U minus is identity minus B minus inverse. Okay, so the inverse of B minus is here instead of B minus, like we had for U for a W minus. Okay, so again, those are functions in H plus and H minus. So we may define, just like CW, we can define a CU operator as, C plus following right multiplication by U minus plus C minus following right multiplication by U plus. And by exactly the same argument like we had for CW, this CU is a bounded operator on the space H nu. And so I wanted just to emphasize here that these, so we have these identities, of course, this is trivial identities here, but if we write out what those mean in terms of the W's and the U's, you get that certain quadratic products like this, W plus times U plus W plus, whatever, are actually linear expressions in these perturbations. Okay, that's handy going forward. But anyway, so we have this bounded operator CU, and so now the proposition here, so we have a complete admissible contour. V is an admissible jump matrix on sigma with a positive polar exponent mu less than 1 with a corresponding admissible factorization. V is B minus inverse B plus. Then identity minus Cu is a pseudo-inverse to identity minus Cw on that space. Okay? So I'm going to just describe some of the steps, but I don't think I have time to go through everything here. So let's just take identity minus the sort of product of these operators and call that K. We really want to show that K is a compact operator. So we just expand it out. We know how this looks, we know how that looks, and we just write it all out. And we're going to try to keep the formula simple, so we'll avoid, for the Cauchy operators, we're going to just not write the contour sigma in the superscript, because we'll fix the contour once and for all. And then we'll also use the symbol M in place of R sub M. And the reason is because there's no left multiplications. So anytime you see a matrix M, that means you're multiplying on the right. Okay. So here's the operator K, just written out explicitly. These are the pieces of it, and then we remember what these things are, and we write them out. So the first line, these are expressions that are sort of linear in the matrices U plus and W plus and W minus and so on. And I just remember this is C plus following right multiplication by U minus is what it means. Okay. And then the second term here, these are all things that are quadratic. There are 4 terms there, and they are quadratic in these U's and V's. But anyway, so now we played some games. So we used the Pomelj formula in the second set of brackets to eliminate, in the first term and in the last term, we're going to eliminate the rightmost Cauchy operators. These ones and this one, we get rid of by Pomelj. So here's one of the terms, and it gets written in this way. And now we notice that here we have a U minus following W minus, but these are right multiplication operators. So that means we really have the right multiplication operator by W minus U minus. Okay, that's a matrix product here now. Okay, and so now we remember that quadratic combination can be written as something linear. So we write it out like that, and now we get these 2 terms showing up here. And these terms are going to cancel some of the terms that are showing up in the first one. That's the point. Okay? So we do a similar thing for the other term in that second set of brackets. And now all the linear terms cancel. And so our K is written as just a sum of 4 parts, which are these 4 things. Okay? And now we're going to show that each one of these K's is a compact operator. And so just to sort of give you a flavor for it, so C plus following C minus is 0, right? That's one of our basic results. That holds on this space H nu minus. And that's the range of this right multiplication operator, or product of right multiplication operators acting on the full space. Okay. So because that's the case, we can write this K1 by adding and subtracting 0. We can write it as C plus following a commutator following W minus. And the commutators we like because we know that the commutators in the right space are going to be compact, okay? Because they're as good as the U minus is. They have nothing to do with how good the function is that we're acting on. It's all about the U minus. So that is going to turn out to be something compact. Similarly, for K4, we can play the same kind of game and write it in terms of some composition of pieces and a commutator there. Okay. All right. I'm going to skip these details. So K2, after some further steps, which you can read about here and ask me about later, K2 can be written with a commutator in the middle of the sandwich like that, and similarly with K3. So then we think about K1. So as we said, this operator here, this is the ordered product of a bounded map from H nu to H nu minus. That's what this is. That's the multiplication operator. Followed by a bounded map from H nu minus to H mu minus, which is where the U minus lives. And that's this commutator estimate. And so therefore it's a bounded map from H nu to H mu minus. And mu is greater than nu. And so now we just apply this inclusion operator, which is like acting like the identity, and that's compact. And so that gets us back into the space that we want to be in, this one, but now we have a compact operator. Finally, by proposition 3, the leftmost factor over here, that's going to get us back into the H nu space at the end. So this K1 is a product of bounded maps, and one of them is compact. And that's all we need because the compact operators are a two-sided ideal in operator algebra. Okay, so K4 by similar arguments is also compact, and then one has to work a little bit harder with the K2 and the K3, but the key point is always that there are these commutators in there, and so those are also compact operators. So we add up 4 compacts, and we get that K is a compact operator. So we may do the same thing. Remember, for a pseudo-inverse, the order should only matter if we get a different compact operator out. So if we do it in a different order, and we call that K prime, we might notice the only thing that's happened is that everywhere there was the letter U, there's now a letter W, and vice versa. So the same argument works with just switching the letters. So K prime is also compact on H nu. So then the corollary of that calculation, that I had to teach through pretty quickly, but the corollary of it is that identity minus CW is a Fredholm operator on the space H nu sigma. And so now, when you have a Fredholm operator, the thing that's interesting to ask about is what is its index? That's the difference of these dimensions. And so here's a formula. This is Shinjo's index theorem. So under the hypotheses of the proposition 10, the index is 0 for this Fredholm operator. So now I want to make a connection with, you may remember the first lecture at the beginning I was writing on the blackboard, and we had Riemann-Hilbert problem A, B, and C. And B was the one that Riemann considered in his PhD thesis, and the scalar problem. And we said it involves multiplication, but it was a scalar function. And somehow that problem did not always have a solution. It depended on whether, when you take the logarithm of that jump factor, you got something single valued on the jump contour, right, on the circle in that case. And that we said it was like the index of the Riemann-Hilbert problem. So in fact, so Shinjo has proven a more general result in this one because he thinks about invertible jump matrices V that might not have unit determinant. And he gives the following formula for the index, okay? So the index, the Fredholm index of identity minus CW, Shinjo says, is n, that's the matrix dimension, times the winding number of the determinant of V, okay? So I just want to emphasize this formula on the right-hand side, in the case when n is equal to 1, this is exactly the same thing that we had in Riemann-Hilbert problem B as our solvability condition, okay, was that the index here was 0. Anyway, so that's his formula for the index. And in our case, we have the determinant of V is identically 1, and so that means that the winding number is 0. So that's the special case. Okay, so the index of our Fredholm operator is 0. So we can. Sorry. Yes. What's capital N? That's the matrix dimension for the Riemann-Hilbert problem. So in the Riemann-Hilbert problem B, n is equal to 1 because it was a scalar problem. So okay.
The winding number of a complex function is the where the range wind around
Mm-hmm.
0, right?
Right.
And then so now is still the scalar function or
yeah, because it's determinant. It's the determinant, right?
Okay.
So that's a scalar function on the contour. Our contour is not a loop anymore, or not a circle. It's a bunch of arcs, but we can still compute the increment of the argument of determinant of V by following the arrows, right? That's what that means. So, okay, so it's possible for us to give a proof, but maybe I will again skip it because I want to get to some application. So, it's not hard. In a lot of problems, these W's, I'll just mention in a lot of problems, these W's that show up are nilpotent matrices. That happens in a lot of situations. And in that case, it's quite easy to give a proof that the index of the Fredholm operator is 0. But I think I will skip that. Okay. All right. So, So this is something I do want to emphasize. So this identity minus CW, it's got Fredholm index 0. By Joe's theorem on this space H nu of sigma. And what that means in practice, okay, is that identity minus CW, although it's a singular integral operator, it behaves in a lot of ways like a matrix, okay, like multiplication by a square matrix. In other words, the Fredholm alternative applies. So that means that this operator, identity minus CW, is invertible on our space, and consequently, we've got a solution X of the integral equation that gives us a solution of Riemann-Hilbert problem 1, provided that the kernel is trivial. Okay, so that's a fact that's got practical implications. It's a test, really. So here's another key result that I want to mention. So this is called the analytic Fredholm theorem. So suppose that A subscript y, that's a family of operators on a Banach space B, okay? And it's indexed by some complex parameter y that lives in a domain of the complex plane. So now let's suppose that A sub y is Fredholm with index 0 for every single y in that domain, and that you may take this a sub y to be an operator valued analytic function of y in that domain D. Then there's two possibilities. Either a sub y is not invertible for any value of y in the domain, or the inverse exists except at isolated points, and it's a meromorphic function of y. Okay? So only poles of finite order, that's all that can happen. So that's the analytic Fredholm theorem, and this is a result that also has practical implications. And I want to stress here that if the factors b plus or minus, or if you like the w plus or minus pieces that show up in the operator, if they depend analytically on a parameter y in some domain D, then in fact this identity minus CW satisfies the hypotheses of the analytic Fredholm theorem. Okay, so analytic dependence in the W matrices, or the jump matrix really, on parameters means that you can apply an analytic Fredholm theorem. Okay, so now I want to apply all of these ideas in the last half hour here to a Pamela 2 equation. So I want to just review a little bit. So we had the inverse monodromy as a Riemann-Hilbert problem. So this is the problem that we had a different number, I think, in the first lecture. But anyway, this is the Riemann-Hilbert problem for Pamela 2 in this Jimbo-Miwa formulation. So we're given some Stokes multipliers, S1 through S6, some scalars, and a number P in the complex plane that are related according to this consistency condition. Okay? So we have these matrices S1 through S6 of alternate triangularity, upper, lower, upper, and so on, and the product should be the identity. So given that, we're going to try to seek a matrix Z of zeta and y, 2 by 2 matrix. Z is going to be analytic for zeta in the domain C, take away the jump contour, which I'll remind you of a picture in a minute. This matrix Z extends continuously to the jump contour from each sector of the complement, taking boundary value Z plus or Z minus from the left and right, and those should be related in this way. So these SJ matrices get conjugated by some exponentials, which I'll also remind you what this theta is on the next slide. That happens on 6 arcs, 6 rays of a jump contour. And finally, the matrix Z doesn't go to the identity at infinity, but multiplied by this diagonal matrix, the product tends to the identity at infinity. So here's the jump contour in the zeta plane for the problem, and the corresponding jump matrix illustrated on each of these rays. And here this exponent theta is just zeta to the zeta cubed plus y times zeta. Okay? Notice the y is coming in an analytic fashion in all of these matrices. Okay, so if we solve this problem, we can get a function u of y as the coefficient c1 of y in our expansion at infinity. So it's defined by this formula here. And then a solution of the Pamela 2 equation is just a logarithmic derivative of that function u of y. Okay. So to make this problem that we just wrote fit into the general theory, there's a couple things we have to do. So one issue is that the normalization condition as zeta goes to infinity allows this matrix Z to grow without bound, because it has a power minus zeta to the p, and minus p as well in the normalization condition. So we can kind of fix this up if we just get rid of that factor outside of some, say, unit disk, okay? So we'll make a new matrix W of zeta y that's equal to Z inside of the unit disk, and outside we'll just peel off that factor, and that makes W tend to the identity matrix now as zeta goes to infinity, because that was exactly the normalization condition that we had on this part. So, okay, so this matrix W now, if we use this formula, we see that W should be an analytic function, okay, in the complex plane. Take away the original 6-ray jump contour, union the unit circle where this factor disappears, okay? And if we take the unit circle to have clockwise orientation, then the jump across the circle reads like this. So plus means boundary value from the outside by clockwise orientation, boundary value from the inside, and this is the discrepancy. It's just because it's here and not there, okay? All right, so this has an effect as well on the jumps on the 6 rays outside of the unit circle. So here's what they look like. So here's the unit circle part. So inside, the jumps are exactly like they were before, but outside, there's this extra minus zeta to the 2p or minus 2p that appears in the jump factor, in the jump matrix. And I just would like to emphasize that it's kind of harmless because it's a power, but here is something that's like e to the minus zeta cubed, okay? So that exponential is totally going to kill this power. It doesn't really matter. But anyway, now we have a matrix that goes to the identity at infinity. Okay, yes? Sure.
So the jump, before you, can you explain the jump across the positive Riemann?
Yes.
The diagonal parts disappear.
Right. Oh, yeah, because this factor here, this factor is not single valued on the positive real line. Is that so? So originally we had, you're saying we had this on the diagonal, and now we don't. And that's because that factor, this one here, this minus zeta to the p, is not single valued unless p is an integer.
And it kills that part.
And it kills that part. Yeah. Yeah. Yeah, so now you'll notice, there's no, I should have mentioned that, but there's no e to the plus or minus 2 pi ip here anymore. There's just identity. So all these matrices obviously go to the identity now as zeta goes to infinity. Okay. But the next problem is that everything we did in our theory has to do with bounded contours in the complex plane, and our contour definitely is not bounded. But that's not hard to fix, because all you have to do is just compose zeta with some kind of a fractional linear mapping of the Riemann sphere. So like you could define z of zeta in this way, and then its inverse is this formula over here. That takes the upper half zeta plane to the interior of the unit circle in the z plane. And so this is the image now of the jump contour in the z plane, and that's something that makes total sense in our theory. In fact, it's a complete admissible contour if we orient the arcs the right way. You see the plus domains and the complementary minus domains in the picture. Okay? So now we've gotten everything into the finite part of the plane. The point zeta equals infinity at which we're putting on our normalization condition corresponds to z equals equals I, which is this point. So this is like somehow this is the point at infinity in the zeta plane. Okay? This is the point at 0 in the zeta plane. That's what's happening. Okay? All right. So this is now, as we said, it's a complete admissible contour. And so let's call this image contour. I'm going to use the notation. It's also called sigma now. So then the corresponding jump matrix v of z on sigma, you get that by just composing the jump matrix for w in the zeta plane with the mapping. Zeta is a function of z. And you take inverses on the arcs that have to be oriented backwards to get the completeness of the contour. So then you can check that the v of z that you wind up with is admissible with every Holder exponent even equal to 1 if you want. Here you've got to just check the exceptional point. So near z equals minus I, that's the image of the origin. The jump condition satisfies the cyclic multiplication condition because those Stokes matrices multiply to the identity. And that's the condition 16 in our Riemann problem. Near z equals I, which is the point at infinity, there you've got the cyclic condition holding because the jump matrix, as we pointed out, it decays exponentially to the identity as zeta goes to infinity. So all of the incoming limit values are all the same. They're all identity equals for that point. And then there are some other ones. There's the self-intersection points that correspond to the unit circle meeting those various rays. And there, what you have to use is the fact that this W was obtained by something which already satisfied the consistency condition by a single valued substitution. So what I'm saying is that if you start with a problem that's consistent, and then you just make some definitions in different parts of the complex plane by multiplication on the right by some factors, then you always preserve this admissibility condition for the jump matrix. Okay, so even if you have to introduce some new jump contours like the unit circle, when we did that, and consequently we have some crossings of rays with the unit circle, you are guaranteed that each one of those points, the cyclic condition automatically holds. It's like a cohomological identity, like that sort of thing. Okay. All right, so now we can take a standard admissible factorization, v of b minus inverse b plus. So for each nu less than 1, the associated integral operator identity minus CW is Fredholm on our new kind of jump contour in the z-plane. And by Joe's index theorem, the Fredholm index is 0. So that means that after we've done these things, we made the transformation from z to w by fixing up things outside the unit circle, and we made the fractional linear mapping to come to the z-plane. Then the analyticity and jump conditions of Riemann-Hilbert problem for Pamela have been recast in the form of our model general Riemann-Hilbert problem in the for bounded contours in the z-plane. However, we may observe that every solution M of z of Riemann-Hilbert problem 1 is, unfortunately, it's normalized to the identity at the point z equals infinity. And if we then make the substitution z of zeta to come back to the zeta plane, then what we're going to get is that our W matrix tends to the identity as zeta goes to minus I over 2. And unfortunately, that's not what I want. I wanted it to go to the identity as zeta goes to infinity. So the point at infinity has been moved by this substitution, by this fractional linear mapping, and so we have to now somehow fix this up. And that's not hard to do either. So we just observed that because this composition v of z of zeta minus identity, it vanishes to all orders as zeta goes to infinity. That means that v of z minus identity vanishes at z equals I to all orders in this quantity. So by proposition 9, the solution M of z, it's got an asymptotic power series expansion about z equals I, and in particular M of I makes sense, and its determinant is 1. So what we're going to do is multiply M of z on the left by the inverse of that determinant 1 matrix. So then you can check that this matrix satisfies all the conditions of Riemann-Hilbert problem 1, but the normalization condition has been changed into that this property tends to, this quantity, tends to the identity as z goes to I instead of as z goes to infinity. And so if we bring that matrix here, this one, back into the zeta plane through the conformal mapping, then we get a function that corresponds directly to a solution of Riemann-Hilbert problem 2, which is the Pamela problem. So we have to, make the renormalization at zeta equals infinity, apply a conformal mapping, solve the problem there, and then renormalize it. Okay? But at the end, we have exactly what we want. So that puts it into the framework of our theory. So now here's an interesting result in Pamela theory called the strong Pamela property, this theorem. So every solution P of y of the Pamela 2 equation with parameter m in complex numbers is a meromorphic function of y. This is called the strong Pamela property because the weaker form just says that a solution of a Pamela equation should have the property that all of the singularities of the solution that can't be changed by changing initial conditions are poles. This is a stronger property. It just says all the singularities are poles. Okay? That's why it's the strong Pamela property. So the proof is this. So suppose P of y is specified by its initial conditions at some point y0. So P of y0 is A, P prime of y0 is B. So then we do the direct monodromy analysis, and we find that the Riemann-Hilbert problem has a solution when y is equal to y0, and the Stokes multipliers exist, and they satisfy this consistency relation 16. So we have our Riemann-Hilbert problem on the inverse side has a solution when y is y0, and that's the sort of point that we need to apply the analytic Fredholm theory to get something useful out of it. Anyway, so the jump matrix V of Z, it clearly depends analytically on y. That's through the theta, which is just zeta cubed plus y times zeta. And this implies that the Fredholm index 0 operator identity minus CW also depends analytically on y. So therefore, it follows from analytic Fredholm theorem that after renormalizing our solution of z equals I, transforming back to the zeta plane to get W, and then looking at the corresponding solution z by undoing this fix-up outside of the unit circle, we get a solution of Riemann-Hilbert problem 2 that's a meromorphic function of y. And that implies that u of y, this expansion coefficient at infinity, is meromorphic, and hence so is p, which is just the logarithmic derivative of u. And I should mention here that u of y can't vanish identically. The denominator here can't vanish identically if p of y0 is a. That's a finite quantity. So that sort of fixes that last bit up. So that's really all we're doing, just applying the analytic Fredholm theorem, and we have this point y naught in our domain complex plane for y, where this Riemann-Hilbert problem has a solution. So having a solution at one point in the domain means that the solution is mirromorphic on the whole domain, and that's the key result. Okay, so that's one application. So more generally, if we don't have this analytic version of Fredholm theory, well, by the Fredholm alternative, we can still prove existence of a solution if we can prove that somehow the only solution, say x0 in our space of the integral equation with 0 on the right-hand side, is the 0 solution, right? So that's saying that the kernel of identity minus CW is trivial. That's the Fredholm alternative. So I'd like to sort of rule out non-zero solutions x0 of this homogeneous equation. So suppose that x0 is a solution of this equation. Let's define a matrix M0Z through this formula. And I'll just say that this formula here is the same formula we use to define the solution of our Riemann-Hilbert problem in terms of x, except there's no plus identity matrix there. That's the only thing it's missing, is the constant identity matrix, which, okay. So let's observe the following about this. So suppose that x naught is in H nu, it's solving our homogeneous singular integral equation. So then m naught, this thing, is the 0 function if and only if x naught is the 0 element of the space. So clearly if x naught is 0, you put it in here and m naught is 0. But now suppose instead that m naught is the 0 function. So then in particular, its boundary value on the jump contour from the minus side has to be 0. So C minus of this thing has to be 0. That's just putting minus on that thing. That's all. Okay. So now we remember the integral equation. So x naught is CW of x naught. That's the homogeneous equation in disguise, right? And CW of x naught is this expression. So by the Plumelish formula, that means that x naught at the end is x naught times W minus plus C minus acting on this property here, and now on this quantity here. And now we recall that B minus is identity minus W minus, and that means that x naught times B minus is this expression, and this expression is equal to 0, okay? So that means that since determinant of B minus is 1, x0 has to be the 0 function on the jump contour. Okay. Yes? No, I proved that I proved that every homogeneous solution of the problem of this integral equation corresponds to a function m0 by this formula, and the solution, if the solution of the integral equation is trivial, m0 is trivial, that's obvious, but it's also true the other way around. If this function is the 0 function, then x0 is also 0. So just putting a formula like this, which defines an analytic function in the complement of the jump contour, in correspondence with solutions of the homogeneous problem.
Okay, so that's bad news. So that means if we have non-trivial kernel,
then there's something like this that's not 0. Right. Yeah, that's right. That's what we're going to use that. We need that pack. Yeah. So, okay, so this formula, this M0 formula, is analytic where it's defined, it's polar continuous with exponent nu less than 1 up to the jump contour, and you can follow the proof that we had for the same formula with identity matrix added to it, and check that the boundary values satisfy the jump condition for our Riemann-Hilbert problem at every single point. So that means that M0 satisfies all the conditions of Riemann-Hilbert problem 1 except the normalization condition at infinity, and that means that modified condition for M0 reads that M0 goes to 0 as Z goes to infinity. Remember, the other one had M goes to identity matrix, and the only difference in these formulas is whether we add identity or not, right? So this one goes to 0. Such a thing is called a vanishing solution of the Riemann-Hilbert problem. And so what we're seeing is that in this Fredholm index 0 situation, Riemann-Hilbert problem 1 is going to have a solution, and necessarily unique, provided that the only vanishing solution of the same problem, in other words, one solution of the same Riemann-Hilbert problem, but it goes to 0 at infinity, is the 0 function. If we can just study the Riemann-Hilbert problem and show the only solution that goes to 0 at infinity of the jump condition is the 0 function, then we know that the Riemann-Hilbert problem has a unique solution. So furthermore, as an analytic function of z for z large, any non-zero vanishing solution, it has to go down like a power at infinity. And so that means that we can multiply this m by something like this and get something that vanishes at a point like z equals I to power p, right? That's very useful because we want to transfer normalization from one point to another in the complex plane, as we've already seen. So, okay. So what I'm saying is that at the end of this, using this fact here, it's enough to say that we have a unique solution of our Riemann-Hilbert problem for Pamela. It's enough to rule out non-zero functions y, w naught of zeta y, the corresponding jump conditions for w, where the normalization at zeta equals infinity is replaced by something like this. So we want to just show that there's no function that decays at infinity like order 1 over zeta and solves the Pamela jump conditions except the 0 function. That's what we like to do. So, the non-existence of non-trivial vanishing solutions at infinity for lots of different Riemann-Hilbert problems is following from a very handy result to know, which is due to Shinjo. Here's the reference to his paper from 1989. So it's called the Shinjo's vanishing lab. So suppose that sigma is a complete contour in the zeta plane that is short symmetric, which means it's invariant with respect to reflection through the real axis, including orientation, so the arrows also have to map by reflection. So suppose that V is an admissible jump matrix on sigma that satisfies these conditions. So if you have a point of your jump contour that's not on the real line, then of course there's a corresponding point that's its image in the other half plane by reflection, and the jump matrices need to be related by this formula here. So this dagger means complex conjugate and transpose. It's the Hermitian conjugate. Okay. So if V at zeta star is V at zeta Hermitian conjugate, right? And if at every point on the real line V of zeta plus V of zeta Hermitian conjugate is positive definite, so then the only matrix function W naught of zeta that's analytic in the whole complex plane, take away the jump contour, continuous up to the boundary, and satisfies the necessary jump condition at every point, also that decays to 0 a little bit faster than a square root, 1 over square root at infinity, is the 0 function. Okay, so it's like Liouville theorem, but for a Riemann-Hilbert problem, something like that. Okay? And now every complete short symmetric contour has to contain the real axis, which seems like a condition, but as usual, you could artificially take the jump to be the identity on the real axis if necessary. And of course, the identity plus its conjugate is 2 times the identity, which is positive definite, so it's hard. So the proof, I'll just highlight a couple ideas in the proof. So the proof is to think not about W naught, but to think about W naught times W naught of zeta star Hermitian conjugate, this product, and call that A of zeta. So because of the sort of, there's double conjugation here, right? There's a star inside the argument, and then there's a complex conjugation of the matrix elements. This second factor is an analytic function of zeta, just like the first one is, okay? So this is an analytic function. It's analytic in this short symmetric complement of this short symmetric jump contour, and A is also continuous up to the jump contour. So the first thing that you check is you just calculate the jump across any non-real arc of the jump contour. So the boundary value A plus of zeta, this is a little bit weird looking, is W0 plus of zeta times W0 minus of zeta star Hermitian conjugate. Now the minus is here because when we do the Schwartz reflection, right, the arrows have to be the same in the Schwartz reflection, and so plus goes to minus and minus goes to plus. That's the reason for that. Okay, but anyway, this is A plus can be written this way, right? And now we apply the jump condition for W, so that's what's going on here. So A plus is W0 minus times V, and then this one here is W0 plus zeta star times V zeta star inverse, all that Hermitian conjugate. And then you do the Hermitian conjugation, and you have this thing in the middle like that. But then we remember, wait a minute, we know something about V and V of zeta star. They are related by Hermitian conjugation, and there's an inverse here. So this is the identity, and here I just have W0 minus, W0 plus zeta star Hermitian conjugate. That is exactly A minus. So A plus equals A minus at every complex point of the jump contour. Okay? There's no jump. So that means you may use some kind of Morera and generalized Cauchy integral argument to see that A of zeta is actually analytic except on the real line, and it takes continuous boundary values from the upper half plane and the lower half plane, and also because these separate pieces were assumed to decay like a little bit more than a 1 over square root, this thing decays like a little bit more than zeta to the minus 1 at infinity, so it's integrable at zeta equals infinity because of this epsilon here. So that means we can integrate along the real line and close the contour in, say, the upper half plane, and we can get this identity. So whether I take the plus or the minus boundary value, I integrate over the whole real line. It has to be 0 by like the Cauchy integral formula. Okay? So there's that. So now what you do is you use the fact that the jump on the real line has the property that the matrix plus its Hermitian conjugate is positive definite. And so I'm going to just skip the details here because I want to continue with the example, but it's not hard to show that under that condition, both of the boundary values of this matrix A on the real line from above and from below have to be 0. Okay? And at that point, all you have to do is analytically continue the 0 up to the next jump contour, which has trivial jump condition and so on, and you exhaust the whole complex plane. So in fact, this W0 is the 0 matrix on the whole complex plane, just under this kind of symmetry condition on the jump matrix. Okay? So a very useful thing, very easy to check, and very handy in application. So people really like this. So I will now try to show an illustration of it. So global solutions of Hamilton equations under some conditions. So the only solution of the P2 equation that really can be considered to be globally regular in the complex plane, as it happens, is the 0 solution, which you get when m is 0. And all the other solutions have at least one pole in the complex plane. So, but in some applications, what's more crucial is whether a given solution of the Hamilton equation is regular for some restricted values of y. So frequently you think of y as a real variable, you're trying to solve a real ODE, and y is a real independent variable, and you'd like to know that your Hamilton function doesn't have any singularities for real values of y. And that's what you mean by saying that you have a global solution, okay? Now in this situation, the vanishing lemma is really useful because its conditions involve some kind of anti-holomorphic symmetry of the jump matrix, and that in turn is going to require that your independent variable y that shows up in the jump condition should be real, or something like that, okay? So here's some examples of global solutions of the Hamilton 2 equation that are defined for all real values of y. There's the Hastings-McLeod solution. It's most important in the case when m is 0, but it's also a global solution for all complex values of m. There are also Ablowitz-Segure solutions that are generalized in the Hastings-McLeod solution. So I would like to tell you a little bit about something called the increasing tree trunquet solution. So suppose that our monodromy, our Stokes multipliers S1 and S2 both vanish. So in that case, the solution P of y of the P2 equation that you get, it's called an increasing tree trunquet solution. And it exists anytime that m is not, anytime that m is not a half integer, okay? So it's got this property that the solution P of y behaves like a square root in a huge sector of the complex plane. Its opening angle is 4 pi over 3. So all except for 1/3 of the complex plane, you've got square root behavior out of infinity. And this is a sort of the biggest possible sector in which you can have this asymptotic behavior. And that's what distinguishes the tree trunquet solution from other trunquet solutions that are somehow pole-free in smaller sectors of opening angle only 2 pi over 3 instead of 4 pi over 3. Okay, so this condition on such a wide sector actually uniquely determines the solution. And so this P of y, it's got no poles for large y and a maximally wide sector of the complex plane, and the complementary sector has infinitely many poles that accumulate at infinity. So it turns out that this solution is interesting because it shows up in some applications where you want to know that under some conditions on this Panelet parameter, which is 1/2 plus p, the solution is analytic for all real y. And that we can prove using the vanishing lemma. So here's a theorem. So suppose that p is a strictly negative imaginary number. So m is 1/2 plus strictly negative imaginary. So then the increasing tree trunque solution p of y of the Panelet 2 equation for parameter 1/2 plus p is globally defined and non-zero for all y real. So for the proof, we just take any fixed p in the complex plane and constant c, non-zero constant c. So then we can conjugate our Panelet matrix Z by c to the power sigma 3. And that affects the Stokes multipliers in a really elementary way. Here's the formulas for them. And so this conjugation also modifies the matrix, or the function u, the potential u, by multiplication by c squared, but that has no effect on p. So since we're only interested in p for our proof and not in u, without loss of generality, we can put in some extra constraints on the Stokes multipliers. And we're going to choose that S3 is this number, 2 pi I p times S6. So that's an extra condition we can put in because of this conjugation freedom. So we take that condition, and then also with S1 and S2 being 0, we look at this multiplicative consistency condition for the Stokes matrices, and that gives 3 relations in addition to the one that we just wrote. They are written here. So now if we relabel S3, we call it tau. From these identities, we see that S4 is written in terms of tau explicitly like this. S5 and S6 are written in terms of tau explicitly like that. And tau, moreover, takes one of only 2 distinct values according to this identity. So there's some ambiguity because it's tau squared, but that's just a sign. And you can get rid of the sign again by the same diagonal conjugation. So since tau squared is a positive number because of what we're assuming about p, that it's a negative imaginary quantity, we're going to assume without loss of generality that tau is a positive number. So we have a positive number solving this equation, p is a negative imaginary number, and then S6, S5, and S4 are written here, and S1 and 2 are 0. Okay. So the jump conditions for Z look like this picture here. So there's no S1 or S2 parts, so there's identity matrices there, and then the jumps are as they show up here, written in terms of this tau. Okay? So the first problem is this jump contour doesn't have the Schwarz symmetry, so we have to fix that. So we make a transformation like this. Basically, we're going to turn the contour on its side. So that's I zeta, where we had zeta before. We're going to rotate everything by this I, and we'll replace y with minus y. And that's because theta, this exponential exponent rather, of I zeta minus y, is the same thing as negative I times theta of zeta y. So it just comes out as a multiplier. And we do some extra conjugation like this just to get some jump to show up over here. So this is now the jump contour for Z tilde. And it's a Schwarz symmetric contour. You just clearly see that. Okay? And we have this normalization that is sort of funny in the problem. Z tilde times zeta to the minus p sigma 3 should go to the identity as zeta goes to infinity. So I need something that has identity normalization in order to apply the vanishing lemma. So just like with our z to w, we have z tilde to w tilde where we peel off that factor like this. So now w tilde will go to the identity at infinity, and there's an extra circle that will show up in the picture. So anyway, so this transformation adds some circle arcs to the jump contour, which we'll take to be clockwise in the upper half plane and counterclockwise in the lower half plane, so that the Schwarz symmetry is preserving the orientation. And now you just look at this jump matrix and you check that because p is a negative imaginary number and tau is positive, the jump matrix for this w tilde satisfies the symmetry condition in the vanishing lemma. So that means that this quantity is uniquely determined by its Riemann-Hilbert conditions, and the same is true by just undoing the transformations for z of zeta y. So that implies that u of y is an analytic function of y. It's defined for every single real value of y. And using this conservation law that defines the integration constant p, and the fact that v turns out to be Schwartz reflected, a Schwartz reflected version of u, that means that you can see that u of y is not non-vanishing as well. So not only does it have no holes, it's also non-vanishing. So then you just remember this formula and you're finished. Okay? All right, so some references here. And this afternoon we discussed the descent.
Can you go back to that picture when you make formal transformation from 6 rays to unit circles?
Yes. This one?
Yeah. Can you show me what is the image of that added circle?
Oh yeah, the image of the added circle is this. So this is the origin in the zeta plane. This is the point at infinity in the zeta plane, and they're separated by the unit circle in the zeta plane, which is this. Because fractional linear maps take circles and lines to circles and lines. So every ray is a circle. The unit circle is another circle, and so on. Yeah.
Then I'm confused. What is the motivation that you have to do this division? Originally you would just want to make the ray diagrams into the finite.
Yeah, so I want to compactify the contour. It's got rays going off to infinity, so I need to pull the point at infinity into the finite complex plane. So now that point is here.
Yes, but you also modify the jump matrix from D to W, right?
Yeah, okay, that's right. But that's because so that's because I want to have I want to have a Riemann-Hilbert problem where I have a solution that is bounded up to the jump contour everywhere, and also goes to identity at infinity. That's what I want to fit our general theory. The trouble is that the z problem was not bounded in the neighborhood of zeta equals infinity, because the normalization condition for it involved an extra factor, zeta minus zeta to the p sigma 3, which is a power. Okay, so that's something that is blowing up at this point. So depending on which sector, so on you're going in, certain columns of the matrix are blowing up as you approach this point. So that has to be fixed. That's the first problem, and so that's where we go from the z to the w. We remove that factor, and that's the purpose of this circle here.
And then the origin is negative I.
Yes, that's right.
So there are 6 sectors coming up.
Yes, those are the 6 sectors in our original picture.
1, 2, 3, 4, 5. And then the last one
is outside, yeah, this. Right.
Okay.
1, 2, 3, 4, 5, 6.
So thank you for introducing the threshold here. As they introduce, so it teaches 2 ways to compute the Whiting number. One is the Whiting number, the other is the vanish number. But I remember once in the paper of Hughes and Hoffman, they tried to solve the problem by reduce the large data problem to small data problem. So since today you also introduce the small data problem.
So I think if I remember correctly, I think what I remember from the Fields and Koitman paper is that they are making that reduction that you discussed at the level of the direct problem. So they take the potential and they break the potential into some pieces.
No, they use it in solving the inverse problem. They approximate, if I remember correct, the inverse, the Riemann-Hilbert problem by rational one. Then
yes, that's also possible, but not
some small data problem.
Yeah, so that you can also do in in the L2 setting, you can use rational approximation for jump matrices. But the rational functions are not dense in the Hilbert space. So that doesn't work in Hilbert topology.
Okay, so Peter, that means you always use the vanish lemma to prove, to give you the existence.
Or you reduce it to a small norm problem. If you
are
have,
going to
yeah.
reduce your power.
Yeah, that's right. So either vanishing lemma or actually, so Joe's vanishing lemma is fantastic. A lot of times you can just look at your jump matrix or maybe some simple transformations and then just see that it satisfies the conditions. That's why people like it so much. But there are some cases where you can't check those conditions, but still you can argue, like in the proof of the vanishing lemma, you can try to sort of brute force rule out the existence of non-trivial vanishing solutions of the jump conditions. And so, using some like a Lindelof principle or something like that, sometimes you can do it brute force. So there's papers where people do that too. But the easiest way is just the theorem is beautiful because it's just you just look at the symmetry and check the jump matrix has the right property and you're good to go.
So are you going to show us how you are trying to reduce your large data problem to small data problem?
Of course. That's what the last two lectures will be about in different contexts. Yeah.
I have a question about the uniqueness. At the last part, you talk about the uniqueness of the solution of the Riemann Hilbert problem. But in proposition 9, page 27, the statement also contains the uniqueness of the series.
I'm looking for proposition. Oh, here it is. Yeah, okay. Well, the unique is in parentheses because I'm saying it's just it's guaranteed to be unique automatically, right? That's something we proved in the last. That's a Lugol theorem argument. So anytime if Riemann over problem 1 has a solution, it's always unique.
So it corresponds to that Riemann Hilbert problem 1.
Yes. Right. So yeah. So 7 is a solution of an integral equation, but every solution of the integral equation produces a solution mz of Riemann Hilbert problem 1, and because of the uniqueness, there's only one such thing. So it's good enough to do that.
When you try to apply the proposition 9, you use the exponentially decay to fulfill the assumption. However, in your proof, you just use only one. You just normalize it by n of I. So
yes.
You just need to.
Right.
You don't need such a strong assumption.
Right, but the image of the point I in the z-plane is the point at infinity in the zeta plane. And in the Panleve problem, the jump matrices decay exponentially in that case, right? As zeta goes to infinity.
Yes.
So that's why the hypothesis is fulfilled in that case. So here you take z naught to be I.
Yeah, I know that. Because first, when you introduce this proposition, I think, why should we have such a strong assumption?
Mm-hmm.
Right? Indeed, in the proof, you don't need it.
No, you don't. That's right. Yeah, you could. Okay, that's a good point. So you could, if you didn't have these w's vanish to all orders, but vanish to some finite order, then you could deduce a corresponding version of this, but you would have to truncate this at that corresponding order, and there would be an error term that would be a little bit smaller, but you couldn't say much more about it. That's right.
Yeah, even when you check how to say that consistency relation, only
yes.
Up to first order or twice order is enough. You don't need vanish to infinite order.
It depends on what you're trying to do.
Okay, let's thank the speaker again.